We chose Godel's incompleteness theorem as our topic for the CS 4510 final presentation. In 1931, Kurt Gödel published his results showing that finding a complete and consistent set of axioms is impossible. These results, proved by Gödel, have had a great impact on the philosophy of mathematics and logic. Gödel's incompleteness theorems show that it is possible to have true statements that are impossible to prove within a mathematical system. So before we look at the theorems and their proofs, we want to establish a few important definitions. So a formal system is defined by a set of axioms and a set of inference rules. For example, if A implies B and A is true, B must be true. A consistent system is a formal system in which a statement and its negation cannot both be true. A complete system is a formal system in which every true statement has a proof. A provable statement is a statement such that there exists a sequence of axioms and inference rules that lead up to this statement. Note that provable is synonymous with derivable, and the two words are used interchangeably throughout this presentation. And a Gödel statement is a statement that is true if and only if it cannot be proven within a formal system. Gödel's first incompleteness theorem formally states that any consistent formal system F within which a certain amount of elementary arithmetic can be carried out is complete. In other words, any consistent formal system will have statements that can't be proved or disproved using the axioms and inference rules of that system. To prove the first theorem, let us talk about Gödel encoding. Gödel encoding provides us a way to go between natural numbers and a sequence of symbols that make up a statement or a proof. We let p sub I represent the ith prime numbers such as 2, 3, 5, 7, 11, 13, and so on and so forth. And we let n sub I represent the symbol converted to its natural number value via some conversion table. The example conversion table is given in this slide. The Gödel encoding is then just a series of multiplications of prime numbers raised to the power of their corresponding symbol value. Here we have an example where we convert the statement 0 plus 0 equals 0 into its Gödel encoding. If we were to convert the statement into a sequence of symbol values, it would be 1, 3, 1, 5, 1. This implies that we want to raise the first prime number to the power of 1, the second prime number to the power of 3, and so on and so forth. Multiplying the sequence exponentiated primes results in the numbers 16,638,930. So Gödel's encoding establishes a bijection between statements and natural numbers. This means that you can enumerate through all possible statements and proofs given a fixed set of symbols just by using natural numbers. This will help with a diagonalization argument we'll be using in a future slide. Let us first look at some function definitions used in the proof. We let A represent a sequence of symbols that is a statement, and we let P represent a sequence of symbols that is a proof. And we also let G be a function that converts statements into their Gödel encoding. And we let proof be a function that verifies whether the Gödel encoding of P is a valid proof for the Gödel encoding of statement A. Then we define d of A, or the derivability of A, as a function that returns true if A has a valid proof within our formal system. Note that d is a function that has a natural number input. This means that d is a function of a single variable. The proof for Gödel's first theorem also relies upon being able to enumerate through the set of functions. This is in fact possible for the set of finite length functions. So think about the bijection between natural numbers and the set of strings of finite length that we have done in class before. And suppose that set of strings describe a function or a procedure or even a computer program. This makes being able to enumerate over the set of finite length functions possible.
At the core of this proof is a proof by diagonalization. Note that this is not a Cantor's diagonalization proof because we are not making an argument about the cardinality of sets. Instead, we use diagonalization to prove the existence of some function and its corresponding output. We let f sub 1 of n and f sub 2 of n, etc. be an enumeration of all possible functions with a single numerical input, and its outputs are true or false. We imagine a table where the columns consist of an enumeration of natural numbers that, through a bijection, can be converted into statements. The rows of the table consist of all possible functions. It must be the case that there is a column where n is equal to the Gödel encoding of the statement stating that you cannot derive the statement f sub x of x from the formal system. Then this implies that it must be the case that the statement f sub x of x is true if and only if it cannot be derived within the system. After an elementary substitution, the statement reads A is true if and only if you cannot derive A from the formal system. Such a statement is called the Godel statement. We will use Godel statements to prove Godel's second incompleteness theorem. By the definition of complete systems, it is clear that F cannot be a complete system. This completes the proof. Thus, we have proved that given a set of axioms and inference rules that exist in a consistent formal system F, there will always exist at least one statement in F that cannot be proved or disproved. Godel's second incompleteness theorem states that for any consistent system F within which a certain amount of elementary arithmetic can be carried out, the consistency of F cannot be proved in F itself, meaning that any consistent formal system cannot be proved to be consistent just by using the axioms and inference rules of the system F. In order to prove Godel's second incompleteness theorem, we start with a Godel statement G within a formal system F. For sake of contradiction, let us assume that the system F can prove its own consistency. Recall that a formal system is consistent if there is no statement such that the statement itself and its negation are both derivable in the system. Since F can prove its own consistency, it can prove that G is true and unprovable within F, since F is consistent. Since F proves that G is true, it implies that there exists a proof for G within F. This is a contradiction. F cannot contain a proof showing G is true, while at the same time proving that G is unprovable. This must mean that our assumption that F is consistent is incorrect, and so F cannot prove its own consistency. Let's look at some of the implications of Godel's incompleteness theorem. One is that there is a novel way of proving a theorem, which is by proving that the theorem has no proof. In other words, you have to be able to show that a function d cannot be created such that it can derive theorem A from a given set of axioms and inference rules. This serves as a valid way of proving that theorem A is true, because if A turned out to be false, you could have a hypothetical computer enumerate through all possible functions to figure out that A is false. Another consequence of Godel's theorem is the question of whether long-standing mathematical challenges are Godel statements and have no proof. Or it could be that such statements aren't Godel statements and they're just hard to prove. Some people have even speculated that the twin prime conjecture and Goldbach's conjecture could be Godel statements.